Hey guys, and welcome to another session on machine learning. Today we're talking about back propagation in neural networks. So the today's session is going to go into the theory behind the back propagation. I have done a video earlier which talks about just a very simple one cell neural net, but this will go into the complete implementation of the full scale neural net with many layers and as many neurons in each layer and so on, but it's more or less an ANN, right? It's a simple, it's not like a LSTM or something more complicated. It's just a simple ANN, but we're going to talk about back propagation with respect to the ANN. So let's look at a very simplistic model. It's not the most simple, but it is simplistic and yet interesting enough where you can see some of the things that I'm trying to show you. You can see the matrix implementation and all the various interesting aspects of the training. So in this case, I have three layered network. The first layer has two neurons and their weights and bias matrices. And then you have the second layer, which is called L1, and then it has five neurons and its weight matrix and the bias matrix. And then finally the output layer, which is L2, and this has also just three neurons and its weight and bias matrix. And my notation, which is fairly important in this case as we go through this, is to understand the notation. So the way its notation works is that the layer basically, the L2, for example, this layer and the output of this layer is Z, and then the activation of this layer is A. And so this all forms a set along with the weights and the biases, right? So for L2, you would get a WL2, BL2. So this side of the weights belongs to this layer, right? This left side of the weights belong to this layer. So WL1, BL1 belongs to L1. And the output also belongs to L1. So ZL1, AL1, these are all belonging to L1, right? So that's how the matrix is notation works in this case. And for L2, the same thing. The WL2 behind and BL2 behind it belongs to this layer, right? So why am I explaining this? Because when you go to like layer I, right? When you iterate over layers, and this is layer I, remember that whatever weights and biases are behind this layer belong to this layer I. The matrices belong to this layer. Likewise, this layer also controls the output and the activation output, which are notated with this layer. So that's how the matrix notation works. For example, just look at WL2. WL2 is here, and it's going from these five neurons to three neurons. So it's got five rows and three columns, right? It's 5 by 3, 5 by 3. And then the BL2 is just these three neurons. So the biases are just B1, B2, and B3. So these would be the dimensions of these W and BL2 when you're talking about the L2 layer. And there's some other notation. So the way the backpropagation works is that we basically train the network with some random weights in the beginning. Then we compute this cost function. And this cost function is computed over this matrix A, which is the final output of your neural net. So this A minus some target matrix, if you square that and half it and basically take the sum over all this, this is your the cost function, the output expectation of the cost. And so the whole backpropagation algorithm is simply optimizing this cost so that you go down the smallest cost possible, and the weights and biases are adjusted to the smallest possible cost. And so we'll try to move the derivatives in a direction so as to minimize this E, right? And then finally, once we have found the derivatives, the partial derivatives with respect to the weight matrices that are in this neural net, we have to, at the end of the epoch, we have to basically take an average of all um, the average of all the changes and then do the final correction. So at the end of the epoch, you make your corrections and then you start the next epoch with the new weights, right? So the weights remain the same across the epoch, and you iterate over all the samples and all everything. And at the end of it, you take and average all the changes in the derivatives that you have collected over all the samples, and then you make those final, by averaging all those, you make the final change onto your weight and bias matrix, and then you're ready to go. Now, one more thing I want to explain here is this Greek eta character here. This eta character is useful because it's a learning rate. Now, when you take the partial derivative kind of lets you know how, which direction to move, and what the slope is. But you don't have to take the slope. You don't have to go at that rate. You can scale the rate. You can speed up or slow down the rate at which you're at the end of every epoch, how fast your machine's learning. So you could speed up or slow it down. And then one more thing, I have used sigmoid activation function in my initial implementation. And that's why this whole theory is basically based on the sigmoid activation function, because it's easier to understand. But you could as well take any other function like tanh and ReLU and change the differentials to include that, right? So this could be very easily converted into differentials for other functions. But that's kind of a simpler and a trivial job at the end of this. So now, and one more notation would be that in most cases, when we take the partial derivative of this e function, the cost function, what we try to do is we go to the output of any layer, right? So there is a special delta L2 or Li notation. This delta notation is basically if you take the derivative of this cost function with respect to the output of any layer, right? So it could be Li, and there would be just delta partial derivative of E with respect to del Z Li, right? So that is a very important notation that you will see used all the way across all these layers. And it's fairly important to remember that. So now that we understand the basic terminology, let's now look at the output layer and try to see how to compute the partial derivatives with respect to the weight and bias matrices. How do we get to the weight and bias derivatives? So the first thing we are going to do here is that we will start our process of getting the partial derivative E with respect to the L2, which is the weight matrix at the very edge of this network, right? This is the first thing that would change. So the way you would take this partial derivative is that you would first take this, like I said earlier, you take the partial derivative with respect to this output, and then you take this jump here. So first you jump from here to this output, and then you jump from here to this weight matrix or a bias matrix for that matter, doesn't matter. So that's what we will try to do here. So first thing, we will take it with respect to using the chain rule, we will take the partial derivative with respect to the ZL2 and then ZL2 with respect to WL2. That's how we'll get to WL2 from E, right? So that's straightforward. Now, how do we expand this? We already talked about this. This part is called, by notation, it's called delta L2, and we'll see how to calculate that. And then this part is basically, if you look at ZL2, its partial derivative with respect to WL2. So ZL2 is nothing but, the AL1 times WL2, right? So, or WL2 times AL1, right? Because that's really what the output here is. It's this weight matrix times the outputs coming from the previous layer. So that's what I fill in here for ZL2. And then when you take the partial derivative with respect to WL2 here, then all you will get is AL1. So what we end up here is delta L2 and AL1. Now, we have got all the variables and all the matrices, but then we don't know if they are in the right format and if the matrix would produce the multiplication here or a dot product would produce the right format. So we will double check that here. So what we have is that partial derivative E with respect to WL2 would be just the format of WL2, and WL2 is nothing but, if you look at WL2, it's a 5 by 3 matrix. So 5 by 3 here, and delta L2, what is delta L2? Delta L2 is a partial derivative with respect to Z, so it should be just the format of this. So that's 3 by 1. And AL1 is basically going from 5, AL1 is basically just 5 by 1, 5 by 1. So if I try to multiply this, it's not going to work, right? Because the matrix multiplication requires that this and this, these two be of the same size. So we have to move this matrix around. And the way to get a 5 by 3 is if I move this AL1 first and this delta L2 after, and I take a transpose of this. If I do that, then I get 5 by 1 and 1 by 3, and these two 1 will cancel out. You'll end up with a 5 by 3 matrix, which is what we want. So that is what we will say the format. Now that you can probably find a deeper mathematical implementation of this, but this is fairly trivial to see that if these two matrices end up here, then the only way they could produce this size is by doing this transformation, right? So this is the matrix notation of getting to the change of based on the cost function, the change that we should induce into WL2 at the end of epoch. Now this is for every sample, we'll compute this, and then at the end we'll average out all the samples. And once you've averaged all the samples, then you can apply this to the WL2 matrix and you'll get the new matrix. So next we look at the same thing with respect to the bias. So when you try to do delta E with respect to BL2, which is here, you're going to do something very similar. You're going to first take a jump here with respect to ZL2 and then ZL2 with respect to the B, right? So those are the similar steps, and then this would produce the delta L2, which is something we understand. But when you try to do this partial derivative, this is the whole equation here. And when you try to take this with respect to the BL2, this is going to yield just a 1, right? So all this disappears. And so you'll end up with just delta L2. Now this is a size of the BL2. BL2 is really out here. So BL2 is just a 3 by 1, 3 by 1. So this is correct. And this is the answer. So essentially we have now computed the, um, I guess, changes in the weight matrix and the bias matrix at the last layer, right? And one thing we haven't showed you yet is how to compute this delta L2. So we'll look at that next. So that delta L2 is really just this function here, the partial derivative of E with respect to the ZL2. ZL2 is the output of this layer. And how do we compute that? So we break it down by chain rule by first jumping to this point, which is AL2, and then jumping to ZL2, right? So that's what we do here. And then this AL2 is basically, if you do this, this is nothing but partial derivative of this function with respect to AL2. And what you would get is AL2 minus T, right? Because this 2 would cancel out and you just get AL2 minus T. And so then the second part of this function is this, and this is A with respect to Z. So that is nothing but a derivative of the sigmoid function, because we've assumed that the activation is sigmoid. So AL2 is just sigma ZL2. And if you take this partial derivative, it turns out that it's nothing but AL2 times 1 minus AL2. So I'm not going to go into the mathematics of how to differentiate a sigmoid function, but you can look up that on Google or Wikipedia, and you'll see the reasoning behind that. But um, just as a quick note, you will end up with this. And in terms of matrix formulation, let's just double check this. So ZL2, you know that ZL2 will be a 3 by 1 in this case, and AL2 minus T. So AL2 is also 3 by 1. So this is fine. This is 3 by 1 and this is 3 by 1. So this is just a straight, it's not a dot product or anything. This is just a position wise or multiplication for these matrices. This is not a dot product or a matrix multiplication of any sort. So then we can generalize this, that for any, this delta function for any layer LF or Li is, well, I guess this is for the final layer. I'm sorry, this is for the final layer. So this delta function for the final layer can be written down in this following format, that it is ALF, which L2 in this case would be the final layer, minus T, which is your target, times ALF times 1 minus ALF, right? So this is true only for the final layer. And in the subsequent slides, we'll also derive this for any general layer in the middle, right? Because when we derive it for this L1, it becomes the generic delta Z function, right? This is a delta Z. So in this case, it happened to be this delta Z with respect to this final layer. And so this has some special properties here. But when we go to the next layer and the next layer and the next layer, there'd be a different equation. So we'll see that in a second. All right, so now, all right, so moving on to this slide, we look at the layer one. And in the layer one, we're looking at this weight matrix on this side. And this matrix is a 2 by 5 matrix. So you can see this is 2 by 5. And then the bias matrix is just a 5 by 1, 5 by 1 here. And then when you look at this layer, you have 5 outputs in your Z and 5 outputs in your A. So those are 5 by 1 matrices as well. And so now that we understand the structure of this layer, let's see how we compute the del E over del Z L1, which is here, the output here, this matrix. It's fairly important, as we have seen, because all the rest of the derivatives like weights biases are depending on this Z. So the way this is computed is that when you take del E over del Z, that becomes Z over L2. And so you jump, the jump point is here. So you jump from here to here, then you jump from here to here, right? And then you jump from here to here. That's how this whole chain rule will work. And so the way we will implement this is that we'll do this by first Z of L2, and this is just a delta L2 function, as we've seen earlier here. The next thing is that when we look at this transform, this partial derivative of L2 with respect to L1, you can basically break it down. I'm missing a bias function, but I guess that is not important at this point. And so basically what will happen is that when you do this partial derivative here, WL2 comes out, and then you just take partial derivative with respect to the AL1 over ZL1, and this AL1 over ZL1, this we have seen the sigmoid function derivative, and this turns out to be AL1 times 1 minus AL1. So let's just double check. This is the output at this point, and we just want to see if this looks at in a matrix format, it looks correct. So E of over ZL1, so ZL1 was just a 5 by 1, and then we've got delta L2 times WL2, and these are just the 5 by 1, 5 by 1 matrices. So let's see if this format is right. So we had 5 by 1 here, but we have, this is delta at this point, delta with respect to L2 is what? It's delta E over ZL2. ZL2 is here, and this was a 3 by 1. So this was a 3 by 1, and then WL2 was a 5 by 3, and these are 5 by 1, 5 by 1. So clearly these are not in the right format. And if we just move this W in the front, so W dot delta L2 would give us a 5 by 1, right? Because 5 by 3 times 3 by 1, these 3 would cancel out and you'd get a 5 by 1 matrix. So the final format then transforms into WL2 in the front, and then we take a dot product or matrix multiplication with respect to the delta L2, and then the remaining are 5 by 1, 5 by 1. They are just position wise multiplication with respect to these matrices. Now remember, we have used sigmoid here, and that's why this derivative works out to be this only because it's a sigmoid. It will be different for other like tan H and ReLU. You could just leave it that, because if you just leave this step here instead of writing in this format, then it'd be just a generic equation. So we end up with this as this green highlighted box is the final form of derivative of any inner layer, hidden layer, right? Because this is not the last layer. So the hidden layer, then this works out to be the final partial derivative, right? So next, let's move on to the derivative with respect to this WL1. And this derivative basically is your jump points remain the same. Now you have already received, you have computed all the way up to this point. So all you have to do is by chain rule, just extend it so that you go from, instead of ZL1, you go to WL1. So that adds this term, ZL1 over WL1. And this first term we know is a standard delta L1. The second term, when we try to differentiate with respect to WL1, all you get is AL0, right? Because this is just nothing but weight times input plus bias, and the bias is not important at this point because this is um, partial derivative with respect to W. So all you end up with is delta L1 and AL0. Now in terms of matrix check, we can see that this, okay, so minor corrections here. This is supposed to be WL1, not ZL1. So if you make these corrections, you can see that this is with respect to the WL1 becomes delta L1 times AL0. And then the format of this, if you look at WL1, WL1 is 2 by 5, delta L1 is with respect to Z, so this is 5 by 1, and AL0 is just 2 by 1. So clearly this is in the wrong format. If we rearrange this so that this comes first, and this is transposed to get a 1 by 5, then this will be fine. So this is the format, AL0 times or matrix multiplication with delta L1 transpose. That would give you the final format of the differentiation with respect to this weight. And then moving on from there to the next set of equations would be for the bias. So for the bias, it's very similar. You have already come up to this point. You just change this term, and instead of this whole thing, it'll be this equation plus bias. And if you try to differentiate, this term gives you 0, and bias will give you 1. So you end up with delta L1. Now, format, is it correct? Matrix wise, if you see delta U or delta BL1, so BL1's format is just this. So it's 5 by 1. And delta L1 is a Z. So Z with respect to L1 and Z with respect to L1 is 5 by 1. So these are both correct, and this format then is okay. So essentially what we have derived in the second layer is a generic solution. So delta E over delta BLI would be this delta Li notation, right? And also if you step back, you can see that this would also give you a generic solution, that delta E over delta WLI would be A Li minus 1 and delta Li minus 1 transpose, right? So this, you can see that when you computed this for L1, you got L0, and you got this for L1, sorry, this is for L1. So delta E or delta W L1, and if you make this Li, this would remain Li, this would remain Li minus 1. And so that's what we will see in our generic equations. And also quickly remember the formats of these equations, which we have worked out. All the equations in the green that you see here, these will be used in our code momentarily as we look at it. So just quickly look through them. And obviously, you can always go back to the presentation and look at these equations. But this is the format of the, when we're going to look at the Python code, these will be the equations that you will see in the code. Okay, so with that, I guess let's dive into the code here. And so the code is available in Bitbucket, and it'll be called ml neuralnet.py. And I have included NumPy and math for some of the functions, like the sigmoid function in NumPy is very useful in doing matrix multiplications, etc. I've also used Matplotlib. Um, if you want to plot your error function, you can do that. I have currently disabled it because that's taking memory, and I'm running this remotely from a shell, so I don't want to pop the graph here. I'm just going to show you this class called nnet, and no, obviously this is sigmoid based right now, and I can add more functions later. But sigmoid is just a math, this exponential function, 1 over 1 plus e to the power minus x, right? And its differential, we know, is basically x times 1 minus x. So that's why you saw that in the presentation slides. Now, when you do the neural net initialization, basically it has some variables, but let's look through some of the bigger things, like this biases a dictionary. We saw that what the biases were: the Z state, which is the output of the neural net, the A state, which is the sigmoid output state. Now we had some of those del notations, right? The partial derivative notation. So this del W is with respect to the weight matrix, and this del Z is partial derivative with respect to the output. So if I just show you one more time, the partial derivative with respect to the, and this Z, del Z is basically the derivative with respect to the output of the neural network for any given layer, right? And the partial derivative with respect to this weight matrix here, this is over del over del W. This is called del W. So in the code, you will see two things, del W and del Z. Z is the output, W is the weight matrix. And then obviously you run through these del formats for the whole every sample in the epoch, and then you average them to figure out what should be the correction that should be made to the weight matrix and the bias matrix, right? So that's basically the init. Now I have a function to add the input layer, and basically when you add the input layer is the very first, or the input where the X comes in from the left side. So that input layer I record because I use it when you start adding the hidden layers. So when you add the hidden layer, it basically adds those, it figures out what the size of the previous layer was, and if it's the input layer, it's that, otherwise it's the previous hidden layer that was added. Because it's important, because the size of the weight matrix depends on the last layer size, right? So you can see here that it's initialized with some random weights in the beginning, and I've just initialized with some random weights and random numbers here, and the size is basically the previous layer size times the number of neurons in this layer, right? And the bias matrix is initialized to all zeros with just the number of neurons. As we've seen, this is correct. And the weights, basically the weights and bias are then initialized with these matrices, and these are obviously index. How many hashes are already added, those layers are added. So we index into the weight and bias matrix through the layer number, and this is just an index to the layer number. So we initialize this in the weight and bias matrices into the hidden layer. And now that we have the hidden layer created, we are ready for the forward pass. The forward pass is just a forward computation. We take the inputs coming in, and we run through all the basically all the uh, weight and input multiplications to get to the output of the neural net. So the input vector is just the inputs coming in. We reshape it to look like the format that we expected, which was, let's say, in our case, first layer was 3. So we want to shape it into a 3 by 1 array, and which is what we do here, reshape it. And then um, we will basically get ready for this multiplication. Um, and so at this point, we basically run through um, the number of layers, which we tend to use this bias. I tend to use this bias.keys because that's easy to see how many layers are in there in the network. Um, so for every layer, what we're going to do is, if it's a 0, then basically the self.weights are being used with the input array, right? So what we are going to be doing is we take a dot product between the weights and the input array, which is what is coming in from the left side, and we add the bias for the very first layer. So first I equal to 0, or the first layer is special because that's the input. Everything else is just the same, and you just take weights and take a dot product with the previous A state, which is the activation state, and then you add the bias. Now, if you've computed the Z state for any given layer, then the A state is essentially just a sigmoid, vectorized sigmoid function of the Z state. That's all it is. It's a matrix transform. Every element is just, you take a sigmoid and you get this, right? So that's your forward pass. And what happens here is that it keeps looping over this till all the layers are done. At the end, the last A state is your output. And so that we are done with the forward pass. And now we can go look at this algorithm called backprop. So forward pass, what it has done is that essentially it has given us the outputs at the end of this whole neural net. Now, you have run a single sample at this point, right? You ran one single X vector, and if you had some random weights and bias matrices, you got some output, the A output on the right side. So what do we do? How do we train our neural net? Now we have seen our formula, right? In our presentation, we saw the various formula. How do you compute the change in this WL2 and BL2 with respect to the the E cost function um, for the final layer, and then the layer before, which we said we could generalize this layer before to any layer with respect to the cost function. So those formula were there. We saw them, um, and then we saw all these formulas. So now the only thing that's remaining in our backprop algorithm is to implement these functions. So how do we do that? So we're going to again loop over basically the first the epochs, right? Because when we are calling this backprop, we are giving the set of input vectors, the set of output vectors, the eta, which is the learning rate, and the number of epochs, right? And this is how the backpropagation will train the neural net. And so that the what happens is that you loop over all the epochs first. And if you've looped over your epochs, in within each epoch, you will have a whole bunch of samples coming from your data set, one X, one Y, and you keep iterating over them, right? So let's just take the very first sample. So in this case, what I have done is just the standard backpropagation algorithm without anything special. Like there's some things that I tried here that you could just randomly pick out of the whole batch or the input set. You could just take a couple samples, or you could just take one sample and do the learning just over that to speed up your backpropagation. But in this case, I have done just the full blown backpropagation, which is like you take every inputs in the set, and then you apply the backpropagation over every single input. So what I do is I will convert this, reshape into the length of the input array by 1 matrix, so that it's just a matrix form of the input, and then I will store that um, into the A state of the very first, right? This is just becomes an A state because the input is an X form, and then we just to use a for loop, we just convert that as a um, activation state as a -1, right? So this helps our for loop. Then we do a forward pass, and the forward pass basically will compute this with respect to this input set all the outputs. And once the forward pass is done, we have computed all the intermediate states, and we have computed the output. So now the output array is available. We pull out the output array, we reshape it to just the right format, which is n by 1, and then we compute the error function. So we compute the error function, and then the error function is basically computed just so we can compute the how good our epoch has done, right? And so this error is something that we will just average over the whole epoch, because there may be thousands of samples in this data set. So this is just one error of one sample. So we're going to compute all the errors, and we're just going to keep accumulating those errors. Now, next we go into the um, all the layers, right? And because we are going to now compute those matrix equations that we had previously done. So what we will do is we will go over all the layers, and then we have two functions. If we are in the last layer, if you're in the last layer, then the equation is this, which is a minus output times a times 1 minus a. Now, if you go in the presentation to the last layer, and you try to compute um, the del z, let's see where the del z is. So del z is right here. So it was just a minus t and a times 1 minus a, right? And you can see that that's what it is. In the last layer, it is a minus t, um, um, a minus t, or actually this is a state is our output, and out array was the expected output. Yes, so this is a minus t, and this is a, and this is 1 minus a. Now, if you're not the last layer, then the equation was slightly different, right? Because it was W L plus 1 times del L plus 1 times A times 1 minus A. So let's just double check that. So here, this was W L plus 1 del L plus 1 times A L1 and 1 minus A. So you can see that W L plus 1 del L plus 1 and A state L 1 minus A state L. This is exactly what we had derived inside our calculations. Now those are for del Z. What we really interested in is del W. So del W is computed as, it's always the same, final or not, it doesn't matter. Any layer follows the same thing. So del W at layer L is AL minus 1 times del ZL transpose. So you can quickly see that for any layer, we can see, let's just go back and just catch the last layer. So del W was basically a previous layer and del current layer transpose. So you can see that del W is a previous layer and del current layer transpose. So this equation then computed the del W. Now that we have computed all the error functions matrices, we're done pretty much. All we have to do is average the del W and del B over all the data sets, right? Samples, all the samples in the data set. And so we just keep repeating this. We throw all these layers into an averaging matrix, which has all the data, and then we keep going. So at this point, we um, will keep going. And then once we have gone through all the samples, we are at the end of the epoch. And then we can average the all the data that we have calculated for the average of del W and del B. And then we can adjust the weights by weight minus the learning rate times the average del W, and bias is adjusted by negative learning rate times average del B, right? So we are now done. And one thing I do at the end is that I check that if the error gets very, very small, then I can basically finish up. So, so that's, and then I basically store all these errors to do a plot at the end to see how my error was decreasing with time. So average error could then be printed. But I think I print the average error at some point while I'm going through the backprop. I'm just trying to see where my print statements are right here. So average error is printed, and then you compute the weights and biases at the end of the epoch. And that's the end. So now what is my data set? For data set, I'm using an XOR function. So 0, 0 produces a 0. This is my input and output data set. When I feed in 0, 0, I should get a 0. When I feed 0, 1, I should get a 1. 1, 0 should get a 1, and 1, 1, I should get a 0. Very simple data set. Now, where I set up my neural net is right here at the end of the code here. So I set up a neural net. I add input layer of the size 2 here because it's an XOR gate. I add a hidden layer of size 2, and then I add a hidden layer of size 1 because that is the output. So essentially, I've just add, this is 2 node and this is 1 node. So I only have 3 total nodes in my neural net. I do the back propagation at this point, and the back propagation gives us the data set in and out. And the learning rate is 0.5 here. You could change it to 0.1 or something. And I do 10,000 epochs. And then I show weights. And then once I have done through my backprop and I'm ready to go, I run forward passes with this trained network for 1, 1, 1, 0, 0, 1, and 0, 0, and I show result at each step to see what happens. So now that we have looked through all the code, we will just run Python over this neural net and see what happens. So I'm going to run for 10,000 epochs. Now you can see that the error rate is decreasing, and the once we reach about 10,000 epochs, this will stop. And now you can see that the output is fairly small for certain values and almost 1 for the other values. So this is giving 0, 1, 1, and 0. So let's just quickly double check that this is actually working. So it gave 1, 1 gave a 0, 1, 0, and 0, 1 gave a 1. Okay, so this is correct. It seemed like the training has learned the behavior that we expected it to learn. So I guess I've come to the end of this propagation episode, and we have seen how the matrix equations were derived, how they were applied to the Python code, and we actually trained a real XOR gate into our neural net, and it works. So that confirms that at least, at a surface level, we haven't tried very complicated problems here, but at least because we have translated the whole neural net into just matrix multiplication, the Python code looks extremely simple. It's not a bunch of, lines and for loops and so on. It's just very simply, just matrix multiply. And then at the end of it, you just basically are applying those equations that we learned earlier. And so it's fairly straightforward to see that, all that we learned in this presentation, we can see all that in practice. So I will provide this code that I have discussed today in the description in my video. And if you have any questions, leave them in the comment section. If you like my video, give me a thumbs up. And please, please, please do subscribe to my channel. I love when you guys subscribe to my channel. It gives me motivation to make more videos. So keep coming back for more stuff here, and see you in another video. Until then, take care and bye bye.